Hi, thanks for joining us for this, I think, fifth video in chapter 11, and this is the first video about mass spectrometry, which again, I hope you're excited about this. It's a really useful analytical tool that helps you determine the weight of a molecule. And then when you think about it, it's a really amazing thing because molecule is a super tiny thing. So this is kind of like a scale that is able to weigh that. Such a small microscopic, I mean, you can't even see with a microscope type of a object, right? And the way that works is often a typical mass spectrometer looks like this. The first thing that happens is you add your sample, and the sample gets vaporized into the gaseous phase. And the reason why that's important is you want to be able to weigh one molecule at a time. And to do that, it needs to be in the gas phase. If it's in a liquid phase, right, your molecule is surrounded by all these liquid solvent molecules, and so you can't do that. So it needs to be in the gaseous phase. So this is really hot, and so the gas molecule, vaporized gas phase molecules going through this machine, and at one point it passes through an area where it gets bombarded by electron beam. It's literally beam of electrons that are thrown at these samples or molecules. And what happens is because the electrons are negatively charged, you will bump off likewise negatively charged other electrons in your sample molecule. And what that does is it makes it ionized. Specifically, it gets positively charged because the electron gets knocked out by the impact of an electron. So hence this type of ionization mode is called electron impact ionization, or EI. And then this charged molecule goes through the detector, and then because it's charged, when a charged thing moves through a space, that creates magnetic field. You might have learned about that in your physics class, perhaps. And because of that, there's these magnets. And the reason why there's magnets is because the bigger the molecule is, the less it cares about some other external force trying to change its trajectory. So it's big molecules that are like heavy with a huge momentum, right? Don't get have their travel path trajectory modified as much by the magnet, whereas small molecules get they don't have very much momentum because they're small and light, and so their travel path gets affected by the magnet a lot, and it's that effect that the external magnetic field has on these traveling ions that sort of get translated into how massive or how light they are, hence mass spectrometry. Now, here's the electron beam that the molecule passes through that we just talked about, electron impact. Because this is negatively charged, and remember, each of these bonds and lone pairs and whatnot are made of electrons, right? Some of those electrons can get knocked out of the molecular orbital as a result. Sometimes that results in knocking off of like hydrogen or some fragment part of the molecule at the same time. So one of these two electrons came from the parent molecule, one of those came from the electron beam. Sometimes, though, all that happens is it just knocks out one of the electrons in the parent molecule, whether it's in a lone pair or one of the bonds. So it results in a very unstable cation. Sometimes, like a bond that's supposed to be made of two electrons now is only made of one electron, and so forth. And as you can imagine, these cations are really unstable. And so for that reason, they can fragment, and that's why even a simple molecule like hexane, its mass spectrum looks like this. It looks very complex, even though this has a very pure sample injected into the mass spectrometry. It's mass spectrometer. Here's the molecular weight of the hexane molecule, 86. Well, that's what you would expect right here, but you notice it's small in intensity because the parent cation is so unstable that it fragments. right? Remember, carbocation is so unstable that it can rearrange. It's the same idea. This can fragment or rearrange to become slightly more stable carbocations, and that's what you see down here. And so for that reason, the base peak, the tallest peak in the mass spectrum, is not always the parent molecule size. So base peak is 57. Apparently that's more stable than the parent cation M+, um, but that's not the molecular weight of this molecule, if that makes sense. Now, the unit here is M over Z, and that's because that stands for mass over charge. The Z stands for charge. Because technically, if the ion has two charges on it, the detection gets the detected mass will be half of that, and hence it's mass over charge. But typically, we're only looking at a single charged ion, so typically you don't have to worry about the fact that charge might be 2 or 3. That becomes important for really big molecules like proteins if you analyze that, but you could assume that these are just single charged ions, at least for a class. And so this is the molar mass. The mass peak is not always the tallest peak. The mass peak is the peak that corresponds with the largest MZ. Now, you might think, well, isn't it the 87, this peak, that's the largest? We'll get to that in a sec, why we know that this is the molar mass and that is not the molar mass. We'll talk about that in a second, but to explain some of those peaks you were seeing in the previous slide, like 71, 57, and 43, that's because of these fragmentation patterns. Now, 57, to be fair, in this case, it's not that it's the most stable carbocation, it's just that this carbocation can be fragmented by multiple pathways, and that's why it's most abundant. When it fragments, you get the carbocation end and the radical with a unpaired electron uncharged species fragment. The uncharged things don't get detected or seen in mass spectrum. It's only the carbocation fragments when it fragments like this. So if you know the parent structure, you could predict what fragments you should see in the mass spectrum. Here's a tool that's really useful for that. I understand, I think everybody should have access to ChemDoodle, the software. Right, like you should be able to get the molecular mass as well as monoisotopic mass of any molecule you draw, and I'll explain how you get to that in a second. But the tool that I want to draw your attention to is this tool. It says molecular weight, or MW. If you use that, you could sort of cut a bond like right here, and then you could look at the monoisotopic mass of the two fragments that result. And that's really useful because, you know, if you have to calculate all these things by hand by adding atomic weights of each atom, you're gonna run into, you know, calculation errors. So this is a nice way to do that. Now, what do these terms mean? Molecular mass is the sum of the averages of all the isotopes, right? And what I mean is, like for carbon, 99% of carbon atoms are C12 isotopes. They weigh exactly 12 mass units, but some of them weigh 13, some of the heavier isotopes. Molecular mass or molecular weight is the average of all of those. Okay, so that's why it's not a clean whole number. Now, monoisotopic mass is the sum of, for each element, the most abundant isotopes only. So often it's a little closer to the whole number, but not always. So that's what this is and the difference. Okay. Now, this is because this is the average. You're not going to see a mass peak that corresponds necessarily with molecular mass. I hope that makes sense. What you would see in the mass spec is the monoisotopic mass, because each peak is a real molecule. That molecule doesn't weigh the average. It's either like it contains either C12 isotope or C13, one or the other, right? So that's that. Now, if you want to call these functions in ChemDoodle, what you do is you go to in the menu, click on structure, and then click on descriptors, and then click on constitutional, and you should see these menu items: molecular mass and isotopic mass depictions. Okay. Now, the speaking of isotopes, right? Let's talk about why you see often the M+1 molecular weight or molar mass +1 or molar mass +2 peaks that are a little tiny on the mass spectrum. Earlier we saw the hexane peak at 86, which is its molecular weight, but there was a tiny peak at 87, right? This guy. Why is that? Well, that's because of the isotopes that are present in this element. Like for carbon, there's a small amount of C13 isotope present, not just C12, right? And that is responsible for this tiny peak, right? Like 1% of all carbon atoms are C13. So if you have 6 carbons in hexane, there's 6 out of 100 chances that your molecule contains a C13 atom. Hope that makes sense. And so for that reason, this is about 6% of the height of the parent structure, because 6 carbons. And that's a kind of a rough math that's useful to know. If you have a X percentage height of a tiny M+1 peak, this is 87, next to a peak, that's likely the C13 isotope, okay, and the X being the number of carbons. Right? This table also summarizes kind of the same things. Carbon C13 abundance is about 1%. All the other ones don't really matter except for these two I want you to pay attention to because that shows up fairly often enough: chlorine and bromine, the halogens. Okay. Chlorine has about 3-to-1 abundance ratio between the lighter to heavier isotopes, Cl35 and 37. So you're going to see 2 peaks that are 2 mass units apart if you have a chlorine-containing compound. And that ratio is going to be about 3-to-1, and you'll see an example in a little while. For bromine, though, the abundance happens to be about 1-to-1 between the lighter and the heavier isotope. So you see about 1-to-1 ratio peaks next to each other, but set apart by 2 mass units, 79 and 81. So here's an example of a bromine-containing compound. The M is 156, but you see this M plus to 158. And notice the intensity is about 1-to-1, and that's because the peak on the left contains the 79 bromine isotope, and the other one, the bigger one, contains the 81 isotope. Okay, hope that makes sense. Now, the fragments over here do not have that M+2 feature because these fragments do not contain bromine. In other words, this fragmentation going from here to there is likely due to the loss of bromine. And again, you don't want to go by the molecular weight, you want to go by the monoisotopic weight or mass, because the molecular weight is the average of these, which is 157 approximately. That's not very useful, but you want to base your calculations either off of 156 with 79 bromine or 158 with 81 isotope bromine. Here's another example of a bromine-containing compound. Here's the molecular weight and molecular weight +2. Now, you do see some fragments that contain that 1-to-1 and +2 signature, and that's because both of these fragments contain bromine, while these fragments do not. Hope that makes sense. Okay. Now, with mass spec, what are the sort of expectations for you as students in this chapter? With mass spec stuff, I want you to be able to determine the molecular weight based on the mass spectrum. That's, again, the largest MZ peak is usually it, but be careful about the M+1 and M+2 side peaks. That's not the molecular weight, right? And you should be able to determine the presence of bromine, chlorine, and nitrogen based on the mass spectra. Bromine and chlorine, we just went over. Bromine, it's 1-to-1, M+2 M and M+2 peak, so it's easy to identify. Chlorine would look like 3-to-1, where the molecular mass is 75 or 3, and then M+2 is 1 or 25. So it kind of looks like this. Here's a peak that contains Cl35, the lighter, and then here's the peak that contains Cl37, the heavier isotope, and it's about 3-to-1 ratio, 2 mass units apart. Now, how do you determine nitrogens? If you have one nitrogen in your molecule, because it adds a hydrogen, remember when we, well, I guess we haven't talked about it. When you add a nitrogen to a molecule, it brings in extra hydrogen because it can bond to 3 things instead of 2. So for that reason, the molecular weight or the molecular mass, even the monoisotopic mass, it's going to be an odd number, like 147 or something like that. Now, if you have 2 nitrogens, the molar mass is going to be unfortunately an even number, and you can't tell. But nitrogen has that unique property. If you have an odd number of nitrogens, you have an odd mass. Okay, if you combine the mass spectrum information with IR, you should be able to determine the molecular formula. And that's kind of what we want to do for the rest of this chapter, or I should say in the next final video. Now, I just wanted to show you the chlorine-containing mass spectrum zoomed up a bit so you know what I was talking about. Here's the M peak, here's the M+2 peak. Now, if you're wondering about these tiny little peaks right next to it, those are due to the C13 isotopes. Okay. Now, this peak at 91 contains the Cl35. This peak at 93 contains the Cl37 isotope. If you're curious, this peak contains at least one C13 isotope, as well as a Cl35 isotope, if that makes sense. So I'll see you in the next video to work out some molecular, learn how to determine the molecular formula from MS and IR spectra. Okay, see you then.